In our introduction to the alpha helix, we said that it's a spiral or helix, a right-handed helix that is, that's stabilized by a lot of main chain hydrogen bonds. And, they are all up and down here, and they make this a very strong and straight piece of building material for proteins. One thing we finished off with was the position of the R groups or side chains. And we said that each one is going to come out from an alpha carbon and project out away like this from the actual helix itself. So in the previous video, we were simply talking about a regular plain alpha helix that could have any amino acids in it. Now it's time for us to talk about these side chains, and I like to do so on the next page. So what we can do is take this same alpha helix that we had and rotate the entire structure toward us so that we're looking end on to the structure. And now we can see what happens a little bit better. Again, each stick is a peptide bond. The connection points between sticks are alpha carbons, and therefore that is where the R groups are going to be. And what we can do is start putting them on here like this and go around to each successive alpha carbon. And what you can see is a beautiful, basically a sunburst pattern where the side chains are radiating out away from the core main chain portion. Now this is really important, and the reason for that is because what we do is we make alpha helices strong with main chain atoms, hydrogen bonds between them, and then we basically paint the outside with all of the different 20 variable groups that we have: nonpolar, polar neutral, polar positive, polar negative, thiols for disulfides, big bulky groups that are aromatic, all sorts of things, and we can create unique columns, unique alpha helices with unique chemistry projecting outward. Really, that's the most important thing we need to say. Side chains radiate out and coat the alpha helix. I want to also go back to what I said about 3.6 residues per turn. Let's write that down again. 3.6 amino acid residues per turn. We can see that a little bit easier. Let's paint on red here for each alpha carbon, and let's count them again. We start here, we go to the first 1, 2, 3. Now if we go to 4, we've gone too far from where we started. So we go 1, 2, 3, and then about maybe 2/3 of the way over, 3.6 right there. That's what we mean by 3.6 amino acids per turn. It's not quite exact integer, but that's okay. And that's going to be a useful number for us. At the bottom of the page here, we have what we call alpha helical wheel diagrams. Let's make a note of that. These are helical wheels. This is an exercise that I like to do, and I think what we'll do is we'll do this one during our in-class time, and we'll see how we can paint on all sorts of different properties, different amino acids with different properties onto the outside of our alpha helix. So let's finish this video by going back all the way to that beautiful protein structure we see here. This is the COVID virus protease drug target, and I just want to point out these purple colored alpha helices here. You can see them everywhere. There's a spiral like these here, and I want to just point out to you, since we just talked about it, that you don't have to draw this on here because you don't have the structure, but notice if the R group, variable groups, are going to be coming out and radiating out away from the alpha helix, notice that one side in a protein might be facing the interior of a protein and the other side may be facing the exterior. That happens a lot. It happens up here as well too. So that's a really good example why you might want to paint a particular chemical property onto one side versus another side. That's a hint for what's to come. And now we'll leave it at that and move on to our next element of secondary structure.